Okay, so it's a pleasure to welcome our next speaker, who's Sang-Jun Park. He's going to talk to us about tensor freeness and sentient unity.
Thank you for your introduction, and thank to all the organizers for this great event, and I'm very honored to have the chance for the talk in this event. So today my talk is based on the joint work with Ion Nikita from Toulouse, France, which is about the tensor version of freeness and the central limits result corresponding to that kind of notions. So the main object in this talk is about the random matrices having the tensor product structure. Let's say that we are taking the matrix X in Mn tensor R, or equivalently the matrix of size n to the R. And we assume some specific kind of symmetry called local unitary invariance, which is by definition the probability distribution of X is the same with that of U, X, U star, where the U are taken from arbitrary tensor product unitaries. So I drew a picture to represent this kind of thing. So for the matrix X, we are doing the rectangular box with several tensor legs, tensor lines, with the R outputs on the left and the R inputs for the right. And for the U, X, U star, we can draw a picture like here, but in this case, the local unitaries are acting on the each single tensor component. So in this setting, we are mainly interested in some limit behavior of this kind of matrices as the dimension grows to infinity. For example, we can ask that what is the limit distribution of xn plus yn, where they are independent local unitary invariant and each having some specific kind of limit. So we are gonna answer such kind of questions by establishing some framework, what we call tensor-free probability. So before doing that, we will briefly review about some results and the notions from the free probability theory, and then for the last two sections, we're gonna present our main theorems. Okay, so maybe we can just begin from the most basic notions from the non-commutative probability spaces, which is by definition a pair A phi, where the A is a unitary algebra and the phi is just a unitary linear functional, which is also called the expectation. And by the distribution of some subset inside A, we mean some data of the family of phi of PWs, where the P are arbitrary non-commutative polynomials in the element from the set of W's. So maybe the three very typical examples of corresponding to this is the first one is about the probability space, where this is the set of classical random variables having the finite moments of all orders. The second one is about the matrix algebras having the normalized trace. And by combining these two notions, we can consider the random matrix spaces as a non-commutative probability space. So with these things, we say that the L sub-algebras A1 to AL is called the freely independent, or the shortly free, if they satisfied whenever we take the L elements, which each of which are having zero expectations, and any of the neighboring elements are coming from the different algebras, then they have their product has the zero, also have the zero expectations. In other words, this means that every alternating product of centered elements are centered. So this definition is not so natural at the beginning, but it turns out that actually this kind of notion gives the universal rule to write the joint distributions depending only on the marginal distributions of each distribution AIs. For example, if we take the two free elements A and B, then we can write some various kind of the joint distribution between A and B in the marginal values listed as follows. And another very important notion in this side is called the free cumulant. And I'd like to first talk several things about the partial order structure between permutations to define this notion. So first we consider about the length function of permutations, which is defined as a minimum number k, such that the alpha can be decomposed as a product between the transpositions k numbers of transpositions. So this gives some very natural geometric structure on the symmetric groups, and then we can check the triangle inequalities for that kind of functions. And so with these things, we can define the relation between the two permutations so that we say beta is less than alpha if some length function relations hold like here. But if you see this, you can note that already one direction of inequality hold because of this kind of triangle inequality. So the equality condition for this means that actually beta is on the geodesic between the identity and alpha. And we denote the gamma p by the first cycle 1 to p. Okay, so then we can now check that this kind of relation really defines the partial order structure on the symmetric group. And specifically, if we regard the set of permutation betas, which is less than gamma p, then we have the very natural one-to-one correspondence between the set of non-crossing partitions NC of P. And furthermore, we can check that they preserve another partial order structures. Okay, so now we assume that our probability space has a tracer linear expectation. Then we can naturally define some functionals phi alpha for each permutations rather in natural way. For example, if we take the permutation 1, 3, 6, 2, 4, and 5, then we can just group each of the elements according to this cycle decompositions and then have the product of the expectations like these things. And similarly, if we consider the full cycle, then this value becomes just the expectation of the product between all elements. And then we can also define for other permutations very naturally. So these things now allows us to define the free cumulant associated to the arbitrary permutations, which is something defined through another relation called the moment cumulant things, which is equated by these things. But actually, there is some tools from the combinatorics called the Möbius inversion, so that we can really recover the formula, the free cumulant kappa alpha through these things. But here we need some coefficient coming from called the Möbius function, coming from the lattice structure of the non-crossing partitions. And then we also denote by the kappa p by the free cumulant coming from the full cycle, which is another very natural notation when you usually consider about the free probability. So one of the very important results of these things is that actually we can capture the freeness condition by saying that every mixed free cumulant vanishes. In other words, these algebras are free if and only if their mixed cumulant is 0 as soon as we can find two elements coming from the different algebras in their input. Okay. And finally, I'd like to mention one of the most fundamental results in free probability theory, which establishes some connection between the random matrix theory and the operator algebra. So specifically, this says that if we take the independent random matrix families, which are unitarily invariant, and then convergent in distribution in this kind of sense, and satisfy some technical condition called factorization properties, then we can show that they are, as the n dimension grows to infinity, they become the asymptotically free, which means that we can define their joint distribution limit exists, and we can calculate their limit as if they are coming from some free element. So this is essentially about the asymptotic freeness of unitary invariant random matrices, and many kinds of the well-known classes satisfying this kind of conditions, including the GUE matrices, hard random unitaries, or the UD U stars, where the DA is something deterministic matrix. And moreover, we have some other class of random matrices showing the asymptotic freeness, including the orthogonally invariant random matrices and the beginner matrices. And rather recently, Gamil-Mar and his co-authors consider the class of permutation invariant random matrices and observe some another limit behaviors called the traffic independence. So this is something new kind of independence satisfying between some class of the random matrices. So actually, we were highly motivated by this kind of result by naturally asking that what kind of independence we can expect if we consider some other types of the invariance. Yeah. So let me directly give our main result in this kind of direction. So actually, we could show the analogous result of this kind of previous things in the setting of the local unitary invariance. So in this case, if we take the independent NR R-part random matrices, such that each of them are local unitary invariant, and then convergent in tensor distribution, and another technical condition called the factorization properties, and then we can show that they show some another independence, what we call the asymptotically tensor free. So from now we want to explain what this kind of new notions should be. So first, by the tensor distribution, we are meaning the set of data average of some another trace symbol, or we are calling the trace invariant, where these trace symbols is associated to the R tuples of permutation in this case. So actually, we can give the explicit formula for this one, but rather it is better to understand these things from the diagram notations. For example, if we take the two permutations, if we take the bipartite matrices and consider two permutations, 1, 2, and 3, and 1 and 2, 3, then we are considering some diagram starting from 3 matrices and connecting the lines, the first line, tensor leg, according to the 1 to 2, 2 to 1, and 3 to itself. And then we repeat the same thing for the second thing, but according to the second permutation. So that we complete this kind of diagrams, and then we can interpret these things as some scalar values. So by the tensor distribution limit, I mean that this kind of limits up to some normalization always exist for this kind of things. Okay, so in order to explain about now the tensor freeness, we first define some abstracted version of the multipartite tensor probability space. So in this case, we define algebraic tensor probability space by some triple A phi alpha. And here, the A and phi is the usual non-commutative probability space with the trivial expectations. And now we further equip some family of multilinear functional, which mimics the previous property of the trace invariant as we defined here. And one of the examples, of course, will be the previous R-partite matrix space equipped with the trace invariant, and more generally, we can consider triple these kind of things where we starting from the tensor product, multipartite tensor probability space, where this is starting from the non-commutative probability space. So from this one, we can define now the tensor-free cumulant. Similarly, some similar way as we define the tensor usual-free cumulant. But in this case, we are associating the value for the R tuples of the permutations, and the relation here also coming from the relation between the beta S is less than alpha S for now each tensor component S. So okay, so we can now define our tensor freeness, so that the unitless of algebras are called tensor free if every mixed tensor free cumulant now vanishes, which means that this value is 0 whenever we can find some tensor component S where this alpha S connects some two different elements coming from the different algebra. So there are several comments about our definition. So as we did for our free cumulant, we can also recover our tensor-free cumulant formula coming from this kind of things, thanks to the again applying the Mobius inversion formula. And if R equals 1, then everything goes back to the usual free probability theory, and we have the freeness is now the same with tensor freeness. And it also turns out that our tensor freeness gives the universal rule to compute our joint tensor distribution, which depends only on the marginal tensor distributions. So in this way, we could define some abstract version of the tensor probability space, and then we could show their limit behavior. So yeah, now it's already the time. I just mention about our central limit theorem very quickly. So the original statement of the free central limit theorem states that if we take the family of centers identically distributed and free elements, then if we consider that they are normalized sum, they have some convergence in distribution in the limit, and then their limit has some universal property to their limit should be always the semicircular element. And because thanks to very nice properties of our tensor-free cumulant, we could also show that if we take some family of identically tensor distributed and tensor-free elements, then their normalized sum also has a distribution limit, which depends only on their tensor-free cumulant of the original ones, where their summations are restricted to some combinatory conditions of their permutations. And yeah, maybe we have some nice applications for this kind of things to recover some known result, rather recent result of about the central limit theorem for the tensor product of free variables, but maybe I can just skip for that. Yeah. So this is what I have done for our project, and I have several other results, but I didn't present it because of the time limits, such as we have some other examples of the non-independent but still showing the asymptotic free and the asymptotic tensor free behavior. And we could show also for some other classes like local orthogonal invariant. And there are some other things to do, such as that there has been very active research in these directions to consider about the random tensors and talking about their freeness or the limit behaviors. So that maybe we can find we can try to find some more integrated theory to include this kind of thing in papers. And then we can also search for any possible applications for the quantum information theory. So thank you very much.